Today, we're going to have a presentation by Dan Roy here on the phone, and he will talk about Kepler's laws. So the three fundamental principles that describe the planetary motions. Anything that orbits about something else, as I understood it. It's a very important piece of physics. That's basically the foundation for your current GPS, satellites, space exploration, and even exoplanet research. Dan kind of promised us a little bit of algebra and calculus, so I'm looking forward to that. But he also promised that he will take special care and provide this very gentle introduction. So don't tune out on that. Of course, stick on. So today, basically, the presentation is we're gonna first introduce Dan a little bit. Then we start with the presentation. If you have any questions during the presentation, please drop them into the chat. And then at the end of the presentation, we'll go back to the chat and we'll address your questions and do our best to answer those. So Dan here on the phone. So Dan is enjoyed a very exciting career in biomedical, aerospace, and software industries, and he's now happily retired. Lives in League City, Texas, close to Houston. Dan leads the monthly STEM parties, both for microscopy, as he was just mentioning, and astronomy for the park services. So he volunteers for the Foundation for International Space Education and also for the United Space Schools program, the USS program. And that program brings 50 kids from 25 countries to Houston for a workshop about the space program. So it's a very exciting piece. You've probably seen Dan posting about it as well. So Dan is our Houston Astronomical Society Education and Outreach Coordinator. And he's also a member of the Johnson Space Center Astronomy Society, also here in Houston. So he enjoys indulging his ignorance, as he says, in a wide range of scientific subjects as a member of the American Association of Advancement of Sciences. So that is the AAAS. And he loves cooking, biking, nature walking, and kayaking, and doing whatever is on his wife's really honey-do list. So I really look forward to his presentation today. So Dan, the floor is yours.
Okay, thanks, Matt. Well, you were talking about FISE. That's really cool. I'm very happy about that. Let me try to find a place. I can never find whatever I want in this system, so bear with me. And my age doesn't help, but this is really cool. I really love it. This is the deal. We are having indeed, as Matt said, 50 kids from 25 countries, and it's from July 13 to 28, 2025. And basically, we put those kids in families in the area. So if you're interested in having family from various countries, kids from various countries, please be aware that typically it develops international friendships, and your kids, if you have kids, can be invited in return. So that's really a nice way to make contact with people from all over the world. And those kids, 15 to 19, speak perfect English. They are very well behaved. And the only thing we need is an extra bedroom so that you can put the kids in there. And you have to drive them at 8 a.m. to UHCL or Johnson Space Center and bring them back at 5 p.m. That's it. So I think that's a wonderful program. I'm very excited by at the idea of the next one. And indeed, that's one of the things I teach there. I teach public speaking, believe it or not. After that, they all speak with a French accent, for better or for worse. And I also cover Kepler's law. So here is why we are here tonight. And before I tell you about Kepler's law, I have to warn you about something. We Europeans love to set the context in historical terms, okay? And one time it was, oh my God, it was 50 years ago. 50 years ago, I got, after my MSCS, I got an advanced class in pattern recognition, okay? It was basically advanced Bayesian statistics on the way to artificial intelligence, actually, 50 years ago. And I get into the amphitheater at Paris' Pierre-Marie Curie University in Paris. And the guy is talking about the Greeks and the Islamic Golden Age. I said, what? I left, I thought I was in the wrong place. So I checked with the office. They said, no, it's the right place, the right amphitheater. So I came back, and indeed, this time he was talking about statistics. I'm telling you this because this is what I'm going to do to you now. I want to set Kepler's time in context, and that means I have to do a little bit of history. So bear with me. Don't hit the leave meeting button yet, okay? So what I want to tell you here is that this guy, Kepler, and his contemporary Galileo, were basically sandwiched between two different eras. The Middle Age, where we had bigotry and all sorts of nasty stuff coming, and that ended in 476 for the Western Roman Empire, disaggregating because of basically old age, and the Byzantium Empire took over, but it was also finished by 1453. And so we're talking about the old time of superstition and bigotry and the new age of the Renaissance, where people, thanks to the invention of a printing press, by the way, Gutenberg inventing the equivalent of the internet in those days, instead of having a very scant manuscript, very rare manuscript written on the skin of animals, he was able to produce very rapidly copies of stuff that was the wisdom of the age and distributing that to interested people of his age. So this is where we have a big difference between the old age, where education was extremely limited, to the new age, where we are discovering what the Greeks, through the golden age of the see, I'm doing it myself. Some guys never learned. The golden age of Islamic civilization, we transmitted this old wisdom from the Greeks of several centuries before. Thanks to that, we are starting to reawaken, the rebirth, if you like, of science and the arts. And that's the Renaissance from roughly 1450 to 1650, and it is followed by the Enlightenment, which is very aptly summarized by the German philosopher Immanuel Kant as dare to understand. So here you have it. The period I'm going to describe, the period of Kepler, is between the Middle Age and the Enlightenment. And the Enlightenment is dear to us Americans, of course, because these guys with the funny names at the bottom of the slide, okay? All those guys, that's what the founding fathers were reading. They were reading those guys. And Montesquieu is missing, but l'esprit des lois, but this is what they were reading. And so the idea is this: when you start to use reason to explain the cosmos, to explain nature, then it is very natural to think that you can use reason to control your economy, Adam Smith, and then you can use reason to govern yourself. And this is the beginning of a new era of self-government. Hope springs eternal. So anyway, so I want to now tell you that reason did not wait for the age of reason and the Enlightenment to be blessing mankind. This guy here, Aristarchus of Samos, back in 300 BC, 280 BC probably, when he was doing his best work, produced a system explaining the solar system. And he already knew, or he already figured out, that the solar system was based on the sun. The sun was at the center of it, not the earth. Well, this guy here, Ptolemy, in 100 to 170, did not get the memo clearly, because he thought that the earth was at the center of everything. And unfortunately, that myth, that bad information, perdured for 14 centuries, until this guy here, Copernicus, born in 1473, produced a model that was basically sun-centric, heliocentric. Now, he was a smart guy, okay? He's looking at you thinking, hey, don't tell people around you too much of that, because that could be hazardous to my health. And so, indeed, he was very cautious. His book, which he prepared 20 years before his death, was not published until the year he knew he was going to die. He felt that the end of his life was approaching. And so first he dedicated the book to the Pope, and for good measure, and then he published it, and then he died. Okay, so he was a very smart cookie. And here is the deal. This is the model here of Ptolemy, with the Earth at the center, and this is the model of Copernicus, but you will notice something. The orbits are circular, and that comes from Aristotle. Aristotle, which was born in 384 BC and died in 322 BC, by the way, that's 4th century BC. This guy felt that nature reflected the perfection of God. And the perfection of God was exemplified by the circle, the perfect geometric figure, and the sphere, which is, again, the same kind of idea. So he knew the planets were spherical, but he thought that because everything turned according to God's perfection, then the orbits of planets had to be circular as well. And this myth persisted from Aristotle time, skipped Aristarchus of Samos, and went all the way to Copernicus, who said, excuse me, no, we have a better way to represent the solar system. Now, on the heel of that enters Tycho Brahe. Now, Tycho Brahe was a Danish astronomer who at the time was living in Prague, Czech Republic now. And this guy was an incredible observer. He made observations, by the way, with the help of his sister Sophie. They made observation to the 1 minute of angle accuracy. Now, that's pretty good, okay, because they did not have a telescope. It had not been invented yet. And they had to rely on basically glorious protractors, measuring angles. Now, his protractors were macho protractors, 10 meters in diameter. I saw one of them in Denmark. And that's of course, the price you have to pay if you want to have precise observations. But night after night, he measured and carefully recorded what he was seeing in his notes. Okay? And that is very fortunate because in 1600, the hero of our story here, Johannes Kepler, a German, refused to convert to Catholicism. So he had to leave his native area, his native country, and take refuge with Tycho Brahe, actually. We invited him to be his assistant. And Tycho wanted him to study the planet Mars in particular because Tycho knew that his model did not fit Mars very well. And so, fortunately, Kepler was hired by Tycho, and Tycho had the good fortune, the good taste of dying the year after that. And that's important because Tycho was very secretive with his beautiful data. He did not want anybody to know about it. And so when he died, Kepler had access to his notes, and he basically stole them because he did not tell the family about that. And the family was too busy arguing about the money because Tycho Brahe was very rich. And they were too busy dealing with who was going to get the jewelry to bother that Kepler was stealing this absolutely pristine data that he used to put together his third law. Now, Galileo, his contemporary, was blessed with a telescope that he had obtained from the Netherlands about 2 years before, and he made his own, by the way, this Galilean telescope. This was a very primitive instrument. It was convex, concave, kind of very simple geometry. And it was, of course, full of chromatic aberrations, but nevertheless, with this about a couple of inches, I believe, a couple of inches instrument, he was able to discover the moons of Jupiter. He was observing the phases of Venus. He was seeing craters on the moon, and the phases of the moon reminding him of the phases of Venus and vice versa. I mean, this is what really made him believe that perhaps Copernicus was after something. He was up to something. Of course, Copernicus knew that was hazardous to his health, and it became hazardous to Galileo's health later on. So this is to set the context, but when you look down to it, the very beautiful observation of Tycho Brahe, even the rules of Kepler, all that stuff, and the model of Copernicus, all that stuff was basically conjecture, okay? There was no mathematics behind it. It was observations, but it was not based on the mathematics, and this would have to wait 1 century more. This would have to wait Isaac Newton to finally put the observations of Tycho Brahe, the rules of Kepler, and the model of Copernicus, part of the laws of nature. So, the first law of Kepler, finally we are getting to it, thank you, of Kepler, is that the planets are not moving in circular orbit. They are moving in ellipses. And that explained a lot already. And if you want to draw an eclipse, that's very simple. You take 2 points here called the foci, and you put a string between the 2 foci. You put a pencil at the end of that, and you go around and you put together an eclipse. Okay. Now, it is very easy to understand that if the foci are in the center of the eclipse, you get a circle. And that would make Aristotle very happy. But the point is this. From the semi-major axis here and the semi-minor axis there, you can compute a quantity called the eccentricity that shows you how ecliptic the thing is compared to a circle. And if you use Pythagoras, you will see that you can easily relate the eccentricity to the minor axis and the major axis. It's basically because the distance between the focal point and the top here is exactly the major axis, m, all right? So that's why you have this relationship. Now, how eccentric are the planet orbits? Well, not very much, actually. If you look at what's going on here, in the solar system, you see that Mercury gets the cake, okay, with an eccentricity of 20%. That's the biggest one. Venus, on the other hand, is basically a circular orbit. And Earth is not bad either. Now Mars is 10% eccentricity. It starts to be more interesting, and that's why Tycho wanted Kepler to have a good look at that one. And Kepler made good use of the observation of Tycho to produce his laws. Now here, I want to show you the solar system seen from above. Mercury, of course, is at the center, followed by Venus. The Earth is in blue, and Mars is in red. And I want you to, in particular, have a good look at the planet Mercury here. It was at aphelion, and it's going to at aphelion. Yep. Well, of course, I cheated, but let me let me play it again. Yep. You can see, I hope, the acceleration at perihelion compared to the slow movement at apohelion, which is what we are seeing here. Now this is important because this is the second law of Kepler, actually. So the first law of Kepler is we have ellipses. The second law of Kepler is more complicated. It says basically if you have a radius joining the sun to the orbit of a planet, the area that is swept by this particular radius is constant in time, equal area in equal time. So here, for instance, at perihelion, the area A1, when the planet is going very fast, when the planet is going very fast, is the same area that at apohelion, when the planet is going very slowly, the area is the same. Now, how he figured that one out is beyond me. It requires very careful observations, of course, that he had, but also it required that he had a model. He had a model of a solar system in 2 dimensions like the one that you see on the slide here. And notice that he never knew the exact distances of a planet. That requires parallax, and that requires a telescope. So he did not have that yet. So everything he did was relative to the Earth. It was all relative distances, but he did quite a lot with that. And he was able to figure out that there is an equal distance, an equal area in equal time, knowing the trajectory of a planet. I mean, for the life of me, this is magnificent. This is really a major step toward reason compared to what you had before the Middle Ages. Now, if you want to go a little bit further, I want to throw a little bit of differential calculus at you, but don't panic. It's very slow. It's very small, and I don't plan to do that again. Now, we are in polar coordinates here. So we are describing the trajectory with an angle and a radius, okay? An angle theta here, and a radius r here. And if you look at the area of the white triangle, the area of the right triangle is r multiplied by this distance here, which is equal to the radius r multiplied by the delta d theta angle here, that's this distance there, r d theta, and therefore the area of a triangle is r multiplied by r d theta divided by 2, or 1 over r square, half of r square d theta. Now, if you are interested in the speed at which this area is swept by, then you're looking at the differential of the area vis-a-vis the time equal half of r squared d theta on dt. And Kepler determined by observation that this dA of dt was constant. If it was constant, it means that d theta of dt varies according to the inverse of r squared. Otherwise, it would not be constant. Now that's huge, because if d theta on dt is inversely proportional to the square of a distance, don't worry, Isaac Newton will make good use of that in due time. All right. Now, Kepler's law says this, the third law says this. The orbital period squared is proportional to the cube of the semi-major axis. My God, again, he could figure that one out. Is beyond me. What he did it took a lot of time to do that, actually. He published, he published the first law. Let me consult my note here, that I don't tell you the wrong thing. He published the first law in 1605, yeah. The second law in 1609. But this third law had to wait for 1619. What took him so long? He had to sort all sorts of combination of mathematics. He tried the square root and the third root and the square and the cubic and the power 5. And he tried all sorts of polynomial. And finally he saw that the square of a period matched the cube of the semi-major axis pretty well. And that's how he was able to put together his third law. A really impressive work of fitting the model to the data. So, how does that work? Well, here is the data that we have today, the semi-major axis and the orbit in years of the planets for Mercury all the way to Saturn, which is the planets that were known in Kepler's time. And by the way, I hope you know what an astronomical unit is, but if you don't, I will tell you. It's astronomical, okay? Basically, an astronomical unit is the average distance between the Earth and the Sun. It's about 93 million miles from you Anglo-Saxons, 150 million kilometers for the rest of the planet. So that's a pretty big thing, pretty big distance. And if you do the computations, you will see that indeed the cube of a semi-major axis is pretty close to the square of the period. Okay, so that's the third law of Kepler. But it would take Newton to really explain that. And here I want to show you a keep it simple, stupid version of, I'm not going to throw the calculus at you because that is the way to do it if you have elliptical orbit. But here I am going to simplify it. And Aristotle will be so happy. He must be clapping in his tomb, okay? Because I'm going to show you a circular orbit. And if you are in a circular orbit, you have the sun here of mass big M, and you have a planet here of mass little m, and it is at a distance r from the sun, and it was going at a tangential speed v here. As per the laws of physics, the centrifugal force that is applied to the planet here, little m, is mv squared divided by r. That's elementary, my dear Watson. Now, but on top of that, Newton told us that the same force that brings m in orbit around the sun is proportional to g, universal gravitational constant, the product of the masses, divided by the square of their distance. That's Newton. Okay, so basically you have the equivalence, if the thing is in orbit, of the centrifugal force and the Newton attraction. Now, that means that v square is basically gm divided by r. The m has the good taste of disappearing in this equation. So it's only dependent on the gravitational constant, the mass of the attractor, divided by the distance between the attractor and the attractee, and that's the square of the distance. But wait a minute, we can easily compute this tangential speed because we know that the planet is going around an entire circumference 2 pi multiplied by r in a period p. So knowing this, v is 2 pi r divided by the period p. So if you put that in this, you square that, and what you get is 4 pi square r square divided by pi square equals gm divided by r. This equation here. So if that is true, then it is obvious, putting the r in the other side, elementary algebra, that r square is proportional to p square and vice versa, because gm on pi r square is a constant. So that is the third law of Kepler, Alan Newton. Is that cool or what? Okay. So if you are trying to plot this now, you may run into trouble, because if you try to put this particular data in a linear scale like this, you see that Mercury, Venus, the Earth and Mars are very clumped together, pretty close to the origin. It's only when you start to talk at Jupiter, 5.2 astronomical unit away, Saturn, 9 astronomical unit, and then of course Uranus and Neptune. This is when you start to have something totally visible that allows you to see what's going on. So there is a better way to represent those enormous distances that we astronomers always deal with. And it goes to the log. All you need is like, the logs are a wonderful invention. It was invented by Mr. Nipper in, when was that, 1512, let me double check when the Neperian algorithm were invented. Well, I forgot where it is, but it was about 16 something. And this guy, Kepler, was a pretty smart cookie. What he did, he decided that instead of trying to be linear, he would be linear with the exponent. So if you have y equal 10 power x, then log y is x, okay? So log of 10 in base 10, of course, is 1. Log of 100 is 2. So you see the idea. Instead of having 1 and 2, you have 10 power 1, 10 power 2. And that allows you to represent the scale I was dealing with earlier in a much better way. 1 billion, for instance, 10 power 9 is just 9. Okay? So you can see that if you have graphs like that, it's going to make huge distances easier to visualize. Now, another thing, and this is why Kepler was dealing with that, is that you can have multiplication reduced to addition. And if you've ever used the slide rule, I have, and I was born in 1948. If you have slide rules, that's exactly what you're doing. You're doing multiplication by adding their logarithms. Now, when you are dealing with a standard coordinate, also called Cartesian coordinate, the equation of a line is y equal ax plus b, where a is the slope of a line. When you're dealing with a log-log graph, you have log y equal a log x plus b, which means that y is proportional to x power a. It's a power law. Now that's very important because remember the third law of Kepler. You know, the square of a period proportional to the cube of the SMA. Well, this is what is going to be represented on a log-log scale. But those logarithms are extremely important in astronomy. Here, for instance, here the magnitude rules. The magnitude is represented by the difference between the magnitude of a star and a reference magnitude, which is Vega, by the way, magnitude 0. 2.5 log base 10 of the ratio. And that is how we determine the magnitude of a star. So a star that is 6 magnitude different from Vega is typically 6 magnitude lower than Vega, is 100 times less luminous than Vega. So when you represent the third law of Kepler in log-log scale, this is what you get. Much better than you had before with a linear scale. You see Mercury, Venus, Earth, and it is nicely separated all the way to Neptune, because here, instead of a linear scale, we have a logarithmic scale of the distances and of the orbital period. Now, by the way, this is also valid for the Galilean satellite, and I will talk about that later. Speaking of which, this is how Galileo found the satellite that were its names. He started with this little thing here, you can see on the left, and he tried to convince people who already believe something else of his discoveries. And as I told you, he pushed it a little bit too much, and that became hazardous to his health. Okay? Basically, his telescope was extremely simple. This is the Lippershey Galileo telephone circa 1608, and you can feel that he had tremendous chromatic aberration with this thing. But you know, if you want the real ray tracing and much more modern design with doublets, this is what you get. But I will not get into that. What I want to get into is that this guy Galileo had a pretty good eyesight. What I did is that I took his book. I took his book, which, by the way, I got from this magnificent gem here by Stephen Hawking. I mean, it's wonderful because he had an entire chapter on Kepler, and it is an absolutely magnificent book. When you can read the authors in their own words. Okay, so anyway, when I took the book by Kepler on what's the name of it? It means the stars at night, the orbits at night, or something like that. you can see that the old man had a pretty good eyesight, better than me clearly. This is what stellarium would show me, and this is what Galileo saw at various time of the night and different nights. And you can see that he had it pretty much right on the money. Sometimes he misses one because there may be clouds or he was not perfect either, but the guy did a pretty good job at representing what he was seeing. And that's why I can show you now the various orbits and of the Galilean satellites around Jupiter. It obeys the same Kepler's laws, and that's why Kepler is so important. Kepler allows you to understand how anything orbits around something else, and that's used to this day to compute the orbit of satellites, to compute the transfer orbits between planets, such as the Hohmann orbit between, for instance, Mars and us, and vice versa. So if you look at the data, the orbital period for Io is 1.76.9 days, Europa is 3.5, Ganymede 7.1. You can see that already you have an interesting relationship here. Europa orbital period is twice that of Io, and the orbital period of Ganymede is twice that of Europa. They are not only tidally locked, okay, like all the moons in the solar system, like all the moons everywhere. They are not only tidally locked, which is they always show the same face to whatever they're orbiting. All the moons in all the universe do that. They are also, in this particular case, in orbits that are synchronous, in synchronous orbits, and they are in the ratio 1:4. Okay? Very interesting. Now, Callisto is not so easy. Okay, Callisto does not obey that trend, but the first inside moon of Jupiter do. And their half major axis here, Io 422,000 kilometers, Europa, Ganymede, and again you can see, and you can see it on the graph, by the way, that you have the same relationship of the third law of Kepler, which means that the cube of a period is proportional to the square of the distance AM of a major axis. And that means that the slope of this curve here, if you look at the equation of in log, the slope is indeed 3/4. And so that gives you an arctangent of 1.5, which is an angle of 56 degrees. Okay, if you want to know all the trigonometry behind it. Now I would like to show you something wonderful you can do with Stellarium. And by the way, I hope that all of you are using this wonderful software because it is free of charge. Okay, the price is right. But it really is a magnificent tool from us. This is what I do when I prepare my star shows. Okay, I always prepare the star party by looking at what I'm going to see. And I go hour by hour to see what's going on in the sky, except that very often, more often than not, it's cloudy. So because it is cloudy, then I can go back to Stellarium and show Stellarium to the audience. See, this is what we should have seen, okay, if the weather had cooperated. So here, I'm going to show you a movie of what's going on when those planets are rotating around Jupiter. Satellites are rotating around Jupiter. And of course, here I am using music. What is the music? I forgot the name of this guy. Let me see if I can. Yeah, Gustav Holst is the name of a guy. Gustav Holst has this particular symphony called The Planet. And here, of course, I am using the Jupiter movement to show you this beautiful ballet of a Galilean satellite around the planet. Okay. Well, what is really interesting to do if you are so inclined, you can do that by yourself by setting the date and time, and then checking the date and time of Stellarium, looking at what the orbital mechanics is doing, and you can indeed double check the number I was sharing with you, and you will be able to redemonstrate the third law of Kepler. Okay, if you're a nerd like me, that's cool. Well, now, Kepler also is the name of a very major observatory that has revolutionized our study of exoplanets. It was launched in 2009, and it has a 94 million pixel speed camera. I mean, imagine that, 94 million pixels. The mirror is only 1.4 meter, but you know, it's about the size of the Hubble Space Telescope. And unfortunately, when we launched it, we reduced the field of view to 12 degrees. So this thing is basically staring at the same portion of the sky, basically outside of the ecliptical plane, and it is looking at something between Cygnus, the Swan, Draco, and Lyra. Okay, so he is really looking at things that are very limited. It observed 500 million stars, mind you, and it discovered 2,700 planets, more than that by today, whose orbit were determined by Kepler's law. Because if you know through the occultation mechanism what the particular period is, then you can compute, relatively speaking, the distance from their star. And that is important to know whether or not they are in the habitable zone, the place where they're not too close from the star, where you basically fry, or too far from the star, where you basically freeze. Okay? And unfortunately, most of those discoveries of those exoplanets are exoplanets that are relatively close to their star, so they are tidally locked. They are tidally locked, so they always show the same size to their star, which means on one side you fry, on the other you freeze, except if you have atmosphere. If you have an atmosphere, all bets are off. That's the case for Venus, for instance. Venus should be definitely very hot on one side, very bad. It's not tidally locked, but pretty close, pretty close. The day on Venus is slightly longer than it's here. Slightly longer. Then it is basically nearly tidally locked. But on Venus, you have the same balmy 450 Fahrenheit, which is, 450 Celsius, which is 900 Fahrenheit temperature on the ground. And that's because of the atmosphere that distributes the heat evenly. So anyway, now we are further than 2,500. The number is 5,500 planets and counting. And now Kepler has died of a good death, and a long-lived test, which is transiting exoplanet satellite system. Now, 5,500 exoplanet and counting. Now, TESS itself has only found about 570 of this, but it has another 7,000 ready to be verified. Because what happens, it TESS find a candidate looking at the deep of the star brilliance, the star magnitude, because the planet is passing in front of it. It's that sensitive. Now it's looking at that, but then you have to have ground-based telescopes, and now fortunately with James Webb Space Telescope and still Hubble Space Telescope, which are still active, you can now have a look to verify that those are indeed exoplanets, that it's not just some kind of coronal mass ejection that you saw from the sun. And we also have a new satellite will be launched. When will we launch this Grace telescope? Let me consult my note. 2027. Okay, we are expecting to launch this beautiful. Now, this is from my alma mater, the Goddard Space Flight Center in Greenbelt, Maryland. That's when they put this thing in the shake and bake. They put the satellites on the vibrating table to represent the very challenging environment of a launch. And also they put it in a thermal vacuum chamber, which is one of the biggest in the world at Goddard, to represent the kind of environment the satellite will have to deal with 200 Celsius on one side and minus 150 Celsius on the other side, like on the moon, this kind of stuff. So this GRACE telescope will revolutionize astronomy yet again, because it is equipped with coronagraph, it is equipped with all sorts of instruments and spectroscope that will allow us to study the atmosphere of exoplanets, like the James Webb Space Telescope is doing today, in more comfortable conditions, because the mirror, of course, is huge, 8 meters. So anyway, this is a very exciting development. And in summary, with great patience, determination, and the help of the Catholic Church, who kicked his butt out of his own country, our hero, Johannes Kepler, was able, looking at the data of Tycho Brahe, to empirically discover that the planets were orbiting their star in elliptical orbit. Then he was able to determine that they sweep an equal area, an equal amount of time in their orbit. And that's really hard to explain that it works. Okay? That's why I prefer the graphs to show you that. Basically, I figured that is very impressive right there. Because again, remember, he did not know the exact distances. The only thing he knew is distance relative to Earth relative to Venus, and so on. So it's pretty impressive. He was able to put that together, but he did. And on top of that, he was able to put Newton on its way to his famous inversely proportional to the square of a distance business by looking at the differential calculus, which of course he did not know, but Newton really discovered that, so he was in a good position to tell. Then the square of the orbital period proportional to the cube of the semi-major axis. This one blows me away. It took him 15 years to find that one out, but it's understandable because he was trying all sorts of combinations. Again, he really did not have Newton yet, but Newton explained it. So, this is what I wanted to tell you about Kepler's law. If you're still with me, and I can see that I did not lose too many people, a miracle happened. That may be that because some of you are already asleep, I don't know, but that's typically what happens to my audience. I really thank you for your attention, and that's all I had.
Fantastic, Dan. Thanks so much. So if you have any questions, feel free to go off mute and speak up. Ask them.
I don't have any questions.
I think people are generally very impressed, Dan.
No, I mean, I just probably scared everybody this slide, so this slide is probably where I lost half of the audience. No, it's not a big deal. Okay, basically, I was trying to explain the second law, and of course, if you have, and this is, by the way, a wonderful class from the name of it. But anyway, it's a wonderful organization. The Great Courses, yeah. The Great Courses is this magnificent class about astrophysics, and this is part of it. And then the professor goes into the real computations with elliptical orbit, and that brings tears to your eyes. I mean, it's great.
Oh, fantastic. Wonderful.
Yeah, a lot of the great courses, a lot of the great course material is really good.
Yeah, it is. And by the way I follow those classes is not by paying the full price. Because I'm cheap, my wife will tell you I'm a cheap guy. And what I do, I have a subscription to a sister organization called Wondrium. and Wondrium for about $180 a year, I believe. For about 180 bucks a year. Wondrium lets you read all you can eat, So that's that's a buffet of sort, and I can have all sorts of classes there, from classic stuff, from literature to philosophy to science, and that's magnificent. That's how I spend my time when I'm not boring kids with stock models.
Awesome. I saw Dean. You
do have a question.
You have a question? Yeah, go ahead.
Are all objects tidally locked within a certain radius?
Oh, that's a great question. Now, there is a certain radius.
Or relative radius, obviously.
Yeah, relative radius. Good way to put it. Now, really, the issue. Let me first try to get rid of that, and I just cannot for some reason. And sure. Okay, here we go. Let me get rid of that, get rid of this, get rid of that, get rid of that. Okay. Now, yes, this is a very good question. There is, of course, an orbit under which, if you are under this orbit, the body disintegrates. Okay. I forgot the name of it. It's a French guy, but I forgot the name of it. Can you remember, Matt, the name of this guy? I should, because he's French.
No, I don't. No. It's a French guy. You should know him.
Yeah, right. Well, this guy, those guys have nothing else to do but to put together laws, and then poor students have to toil for decades on that stuff, But anyway, this is an excellent question, and I don't know the answer to that. But there must be there must be some kind of distance under which you have this tidal effect, and I just don't know the answer. Sorry.
I had a kind of a related question, so I'm going to take the liberty to follow up with myself. So does that mean, following that we just learned about the Kepler's third law, that for planets to be habitable, you need to have a certain distance from the star, and therefore, looking at the period of the transit, there's a certain period that is just too quick, right? Because it infers that the planet is too close to the star, so it will be tidal locked, and therefore it will be uninhabitable. So could you infer from the period, if you have a tidal lock, and then that therefore this planet is one side very hot or very cold?
Well, yeah, that is indeed why this question was so excellent, and I'm sorry I don't know the answer to that, but most of the planets we have discovered, of course, are very close to their star. There is a good reason for that. We are not patient. Basically, all those stars are going so close. All those planets are going so close to their stars, so they basically occult the star every couple of days, couple of weeks. So we are able to see the dip. But if it is like Neptune, some 200 years, that's another story. You cannot easily see that. And we don't have 200 years to wait. So unless we have better telescope and interferometry to really determine the orbits of those things, which would require tremendous sensitivity, then we cannot easily do that. Now, the reason why we call that habitable zone is very misleading. We call that habitable zone because based on the thermal properties, based on the energy emitted by the star, we can determine knowing the distance. If there is a chance, should water be present, that water would be liquid, and preferably at the triple point of water, okay, which is where water can be liquid, gaseous, or solid. This is what we have on Earth. Why? I'm glad you asked. because basically, if you have water, you may have life. Because if you have water, if you have nutrients, and if you have a source of energy, you have the three conditions necessary to have life evolving on this planet. But that is a lot of ifs, okay? And so far, we have absolutely no proof that there is life anywhere else besides Earth. We have tentative points to consider. We have data from Cassini spacecraft at Saturn with a itsy-bitsy world of 200 kilometers diameter called Enceladus. This thing has water vapor, dirty dirt, from the surface of a little world. And Cassini flew into it. First time it went into safe mode, by the way, but it flew into it and was able, through the spectroscopy, limited spectroscopy it had, to determine that this was not only water. You had really large molecules there, hydrocarbons. And that is extremely exciting coupled with the fact it has hydrogen, because hydrogen is like candy for a lot of microbes. So we have some elements, and on its way to Jupiter are two spacecraft, JUICE from the European Space Agency and Europa Clipper from the US, that will arrive in 2030. And those things are going to really look very close at Europa and at Ganymede. Now, Ganymede is bigger than Mercury, so that's a pretty significant loop. But Europa is slightly smaller than our moon. But Galileo, another spacecraft that was launched in the 90s, has determined that there is a magnetic field disturbance at Europa, which indicates a subterranean ocean. There is an ocean in Europa that's twice as much water as on Earth. So we are salivating looking at what those spacecraft will find, because they have extremely sensitive equipment, like a magnificent mass spectrometer, mass specs, and other ice penetrating radar that would allow us to really have a look at this little world, and maybe there will be evidence of life on this world. Now, I don't expect dolphins, but reaching from the surface. That would kill them in an instant, actually, because of the radiation of Jupiter. But there will be some mechanisms to determine for all those instruments that they have enough nutrients, enough compounds that we can see on the surface, for the spectroscopy analysis, and for the ice penetrating radar, knowing the width, the depth of ice to protect the whatever microbes there is from the radiation of Jupiter. We'll be able to tell if, whether or not, this thing is habitable. Now, to see the little dolphins or whatever octopuses at the bottom is another story that will have to wait another century, probably.
Wow, Dan, that's so exciting. Wow, fantastic.
We are living in exciting times, yeah.
Yeah, absolutely. I can't wait. I can't wait. Fantastic. Do we have more questions from the audience?
Maybe they all left when I told my story about the Greeks, which is what I did, 50 years ago, when that guy was going on and on with the Greeks and the golden age of Islam. I'm at the wrong place. Get out of here. Okay, guys, well, thank you very much. It was a pleasure to not talk to you.
Absolutely.
But you have my email. Let me see if I can resurrect that first slide here.
Yeah, Dan, thanks again. Thanks so much.
That's my email. So if you have changed your mind, you want to talk to me, this is where I am.
Absolutely. Thank you so much, everybody. So we're going to close off the meeting. Dan, again, thanks so much. There's so much exciting stuff going on here, and I couldn't wish for a better explanation of Kepler's law. I always wondered how that worked. So and now I get
cool.
it. Now I get it. So thanks so much. All right, all take care. Have a nice evening. Thanks. Bye. Bye.